So with this quick introduction, now let's focus on the directional procedure for determining the wind load on main wind force resisting system only. So we will be focusing on main wind force resisting system and also the directional procedure. And in directional procedure also we will be focusing only on part 1, which is applicable to buildings of all heights and which prescribe the wind pressure in the form of the specific equations which we have to use for all the exposure areas of our building. So this is our focus, chapter 27, for this particular session. So we have two equations which can be used to determine the wind pressure. So let's quickly go through the notation first. P is the design wind pressure, which is our ultimate output which we want to calculate for each of our exposure surface. And this also is the same thing, but this expression on the left hand side is applicable to enclosed and partially enclosed rigid and flexible buildings of all heights. So this expression, this one, is applicable to enclosed and partially enclosed. Obviously there will be a step during the process where we will classify our building in any of these three categories: enclosed building or partially enclosed building, and then third category is the open building. So this is called enclosure classification, and we will perform that classification, and there is a very specific guideline about how to classify our building in any of these three categories. So we'll discuss that in next few slides. So if our building according to that requirement is in enclosed or partially enclosed category, then we will be using this expression on the left hand side. But if our building qualifies for an open building, then our expression will be simplified. It is simply the expression on the right hand side of this slide. So actually if you look at this construction of this equation, the pressure, wind pressure P, is actually a product of three quantities. One is the velocity pressure, which is denoted as Q, this velocity pressure, and then one is the gust factor. I'll discuss in a moment what effect it accounts. And then there is a pressure coefficient. Pressure coefficient for external pressure and internal pressure is different. For external pressure it is denoted as Cp. For internal pressure it is GCPI. And obviously if your building is enclosed and partially enclosed, you may have a significant internal pressure also, and therefore you have the main external pressure minus the internal pressure. This will be your net design wind pressure. But for open buildings, there is no separate internal pressure coefficient, so you directly have to use the net pressure coefficient, which is denoted here as C sub n. Gust factor is same and velocity pressure is same. There are two symbols which are used for velocity pressure. One is Q sub Z and other is Q sub H. So actually it is same thing, both are velocity pressure, but they are determined at different heights. Q sub Z means that this pressure is determined at any general height which is equal to Z. But Q sub H means that it is the same wind pressure but determined at the roof of the building. So H denotes the roof level of your building. So actually it's same thing, it can be determined at any height. So when it is Q sub Z, it is determined for each height a different number. But when it is QH, it is the wind pressure determined at a fixed height, and that height is the roof level of your building. So for velocity pressure, this Q, for windward walls, you will be determining it at different Z heights denoted by Z. But for windward side, you will be determining it for the roof level of your building, so it is determined as Q sub H. Windward side, windward wall is the wall which is facing directly facing the wind. So for example, if this is your plan view and this is the wind direction, so this one is the windward side and the opposite is actually the leeward side. So for leeward side, you will be calculating velocity pressure at the roof level of the building, but for windward side, you will be calculating it at different levels, different heights denoted by Z. Then we have gust factor. Sometimes for flexible buildings, it is denoted as G sub F, indicating that it is for flexible building. For rigid buildings, which are generally defined as the buildings having a time period, fundamental time period less than 1 second, it is denoted as capital G, and its value is generally recommended value is 0.85. So this velocity pressure is actually the main input in this expression, either for partially enclosed or enclosed building expression, or if it is for open buildings, we have QH. So at any height Z, we can determine this Q value using this long expression, and it has an empirical coefficient and then a series of other coefficients or factors kz, kzt, kd, ke, and then velocity design velocity scale. So basic wind speed is one of the main input in that, and then after that we have four coefficients. First is the velocity pressure exposure coefficient. Then we have the topographic factor. Then we have the wind directionality factor, and then finally the ground elevation factor. So four factors which I'll explain in next few slides. They should be used along with the basic wind speed for your particular site to finally calculate the velocity pressure, and then you can put that in this long expression along with the gust factor and external or internal pressure coefficients to finally calculate the wind pressure. Then once P is determined, then you can convert it into design wind forces depending upon the exposure area of your building, and then apply it to perform the wind analysis, equivalent static wind analysis. In case of open buildings, the expression is relatively simple. It only requires the determination of velocity pressure, gust factor, and the net pressure coefficient. The guidelines about both the external and internal pressure coefficients and the net pressure coefficient are available in ASCE 7-16 in chapter 27. We will go through these expressions or guidelines also. For this particular topographic factor, it is again determined from these three coefficients K1, K2, K3, which accounts for different aspects of topography. So these K1, K2, K3 can be determined using a figure and a table, which I'll show you, and depending upon your particular case, depending upon height of your escarpment or your hill or your ridge, you can determine these coefficients and then put that in the equation to calculate kzt. If your topography is not following, or it is not exactly fulfilling the requirements prescribed in this particular coefficient, then you will take this coefficient equal to 1. So we will see that in a minute, what are those requirements to use this topographic factor. So these are the calculation steps to finally calculate the wind pressure P, which I just showed you in the equation. So in order to calculate that P, you have to follow all of those calculation steps. So first you start with the determination of risk category of your building. This is a concept which is common between many of the type of loadings, for example seismic loading or wind loading and other types of loading also. So depending upon the risk category of building, which again depends on the occupancy type of your structure, you have different requirements for wind loading and also for other types of loading also. So first step is to establish the risk category of your building. Then you have to determine the basic design wind speed V, and it will be depending on the applicable risk category. So there are different figures which are available in chapter 26 to determine the basic wind speed for different sites in US, and you will see that those values are dependent on the risk category of your building. Then step 3 and all of those associated steps, they are related to the determination of those coefficients which are required to determine the finally pressure, internal pressure coefficient, other coefficients. So we start with the wind directionality factor KD, then we classify the building based on its exposure category, then topographic factor KZT, ground elevation factor KE, gust factor, enclosure classification, whether your building is enclosed, partially enclosed or open, and then finally the internal pressure coefficient GCPI. Then step 4 is the determination of velocity pressure exposure coefficient. Finally, the velocity pressure determination KZ or QZ or QH. Then external pressure coefficient CP or CN, depending upon whether your building is partially enclosed or enclosed. So this is for enclosed or partially enclosed, and then this CN is for open buildings. So for different cases there are different figures available to determine these coefficients, and then once you have all the input required to determine wind pressure P, so in step 7 you can use that expression which I showed earlier to finally determine the wind pressure. So equation, the left equation which I showed is for rigid and flexible buildings, and then right equation which I showed is for open buildings, the simplified equation. So let's sweep through all of these steps quickly, because we also have to have a software demonstration for the same ASCE 7-16. So we'll see that we have to provide these coefficients using these tables and figures in that program, and it automates those two equations for us. So depending upon whether our building is open or enclosed, the program actually uses these two equations to determine the wind load at each level and then perform the automated wind analysis procedure for us. So let's sweep through all of those calculation steps which we have just seen. Step 1 was to determine the risk category of the building. So depending upon the occupancy type of your structure, you have to select 1, 2, 3 or 4 risk category. 4 is the most severe risk category, 1 is the lowest risk category. 1 is defined as a building or other structures that represent low risk to human life in the event of failure. So if you have a warehouse or any other structure in which no one is actually residing, then you may go for risk category 1. Similarly, for risk category 3, if you have a building or structure where the failure of which could pose a substantial risk to human life, you can assign a risk category 3 to your building. And similarly, for essential facilities, for hospitals, for schools, for example, or some other important structures, you can assign for risk category 4. If your building doesn't lie in 1, 3 or 4, you give a risk category of 2. So that's how you, depending upon the intended occupancy of your structure, you assign a risk category to your structure. This is the step 1. All of the other steps onwards, for example, the determination of design wind speed, it depends on the risk category of your building. So that is step 2 actually, determine the basic wind speed V. So for that, for US, we have these figures starting from 26.5-1A up till D. So we have figure A for risk category 1 buildings, a separate figure to determine the design wind speed for risk category 2 buildings, then separate for 3 and then 4. So let's quickly go through these figures in ASCE 7-16 and then come back here, because I actually want to show you the criteria on which these figures are developed. These hazard maps for the design wind speed are developed. So here I have ASCE 7-16. So let me directly go to chapter 26, and in that particular figure to show you how the wind hazard map compatible with the ASCE 7-16 definition of wind hazard look like. So let me go to chapter 26 directly. This is chapter 27. Okay, these maps. So let me directly go to. So this is the guideline about the figures 26.5-1A and -2A. These are for risk category 1 buildings. So yes, this is 26.51A and this is for 1A is continued from previous figure. So you can see here that this figure for risk category 1 is in the form of wind velocity contours, and they are in two different units. Obviously, the more importantly, I want to highlight here that first of all, these values are the nominal 3-second gust wind speed. So actually miles per hour is in outside the parentheses, and then we have the meter per second velocity in the parentheses. So these are 3-second wind gusts, so which means that at any particular 3-second duration, this is the maximum number recorded, and this is the standard hazard definition for design wind speed in this particular reference. And not only this particular you can say requirement that it should be a 3-second gust, it should be recorded at 33 feet, which means 10 meter height above the ground for exposure category C. Exposure category C I'll explain in next few slides, because there is exposure category B, C and D. So I'll explain what C means. So if your site is located in between two contour lines, you may use linear interpolation. So and then there is a guideline about other areas which may not be covered in these contours. And then more importantly, the wind speeds correspond to approximately a 15% probability of exceedance in 50 years, which actually translates into the annual exceedance probability of 0.0033 or mean recurrence interval of 300 years. So this is the hazard level which is set for risk category 1 buildings. You will see that in next figures for risk category 2, this probability of exceedance will reduce, which means for buildings having a higher risk category, the hazard level which is set as the definition of design wind speed is also higher. Mean recurrence interval will increase and the probability of exceedance in 50 years will reduce, right, for higher risk category buildings. So let me go to next figures for any of the building which is for risk category 2. Yeah, these ones. So the same figure showing the same contours, having the miles per hour value in outside the parentheses and meter per second in the parentheses, the value of design wind speed V. It should again be for 3-second gust, recorded at 33 feet height or 10 meters for exposure category C, but it should have a probability of exceedance 7% in 50 years, which translates into a mean recurrence interval of 700 years. So a higher hazard level is set for risk category 2 buildings. For risk category 3, if we go to next figures, yeah, this one. So you see here that now the probability of exceedance is further reduced 3% in 50 years, corresponding to 1700 years of mean recurrence interval. And then finally we will have a Risk category 4, these ones, essential facilities. So you see 1.6% probability of exceedance in 50 years, corresponding to a mean recurrence interval of 3000 years. So which means that there is a 1.6% probability that in next 50 years you will encounter a wind speed higher than this number which you are picking from this particular map, right? So as the hazard level increase, the probability of exceedance is reducing. So same concept as we use in the performance based seismic design, that we have different hazard levels, DBE level, MCE level, etc. And we expect that our structure is going to perform for each hazard level in a satisfactory manner. Here, the hazard level is dependent on the design hazard level is dependent on the risk category. So let me go back again to the slides and proceed to the next step. So it is expected that the national building codes of different countries, they provide the wind design hazard maps in their national building codes, which is compatible with these definitions if they want to follow ASCE 7-16 procedure to determine the design wind pressure. So these are important notes which you should consider, that this V, this basic wind speed cannot be any number. It cannot be hourly mean wind speed. It cannot be recorded at any height. It should follow all of these guidelines, and then it will be compatible with the ASCE 7-16 expression to determine the design wind pressure. So we have different definitions of wind speeds, but we should keep in mind that this particular 3-second gust wind speed is the one which we should use as the design wind speed. We have the sustained wind speed, which means the average wind speed over an interval of 1 minute, for example. And then we have an hourly mean wind speed also, and some other definitions of wind speed. But 3-second gust is the one which should be used. And then there are different empirical expressions also available, which can convert approximately a wind speed which is determined over a different interval into another wind speed which is the maximum number in any different interval. So there are expressions available which can convert the sustained wind speed into 3-second gust, but obviously the final wind hazard definition should follow this definition.